Good morning. This is Monday morning, the 17th of October, 2016, 9:32 in the morning, Calculus 2, and right now I'm the only one in the room. So I'll start from the current slide where we left off last time. Normally I'd ask if there are any questions, but nobody's here to ask. So the last thing we did was the slide, last thing we did was example 4, but they mentioned from example 4, they gave us a solution, which was, and I'll write it on this slide, even though it has nothing to do with this, but example 4 was the integral of sine 4th x dx. Okay? Now, the solution we got, carrying out the way we did, was 3/8x minus sine of 2x over 4 plus sine of 4x over 32 plus some constant c. Okay? But then they make a comment at the bottom, or just below that, that if you used the formula I think that we derived in the previous section, I believe it was, or wherever we did, I don't remember exactly where, and use that recursive relationship, that's what it was, and you did it that way, you got sine 4th x dx was equal to negative 1/4 sine cubed x cosine x minus 3/8 sine x cosine x plus 3/8 x plus c. Okay. Now, a couple of things to note. First, these terms are identical, so they're the same. Of course, the c's are identical, so they're the same. Those middle two terms that aren't. And why is that? Well, notice this one we have values, trig functions of x alone. Up here we have double and quadruple angles. Well, that's because, as they say here, trigonometric integrals can be expressed in many different ways because trigonometric functions satisfy a large number of identities. If you use the double angle formula on this term right here, then you're going to wind up with something that relates to the one below. And if you use it twice on that one, you'll wind up with those that relate above. And when you combine them all together, you'll find out they're the same answers. Okay? And it said you can check that this agrees with the result in example 4 in exercise 63. Okay. Now, the next thing they do, and why they don't have this in a slide, I'm not sure, but they don't. I'm going to turn on the light because it's sort of dark on this side. I kept thinking a student would come in and we turn on the other lights, but since no students are here, I have the projector off, but I am recording, so it will be out there. They don't have a slide on these cases. When they're integrating, I think I'll clear this slide so you have a little bit, won't be as confusing. And the thing is, this is still on here, but don't worry about that. Okay? Now, when you're integrating sine m to the nth power x cosine to the nth power x. Okay? There are three cases they mention here. Case 1, that's when the m is odd. And actually this would work for either being odd, but it's if m is odd, then split off one of your sine functions. And then you're left with m sine to the m minus 1, which is then even. Okay? Well, in that one sine function, you know that is the derivative of minus cosine. Okay? So the rest of those sines you can split up as because as some multiple power of sine squared, okay? And when you do that, sine squared is 1 minus cosine squared, and then that traces to whatever the power is that's left, and you can expand that binomial, as big as it is, multiply that by cosine nx, and you have everything in terms of cosine with 1 sine x dx, that being the derivative. You can go and use substitution and solve that. Okay? Split off 1 power of sine x, use sine squared x equal 1 minus cosine squared x, express the remaining powers of sine x in terms of cosine x, then substitute. U equals cosine x, du is equal to minus sine x dx. Go to that. Now, case 2. N is odd. Okay, like I said, this works either way. Split off 1 power of cosine, then that leaves your cosine n minus 1 of x, which is even. Take that 1 cosine, leave it with the dx, and you know already that derivative of sine is cosine dx. So you have exactly what you need there. The rest of your cosines are even. Make that cosine squared x raised to whatever power it takes to come up with that even number. And cosine squared x is 1 minus sine squared x. Expand that binomial by whatever power you had left over. Then multiply it by sine x, and you got everything in terms. Do a substitution. Let u equal sine x du is cosine x dx, and you have a power series, just like before. Now, case 3, that's the tough one. Case 3 is when m and n are both even. That's the more complicated case. Okay? Now, either use the double angle formulas repeatedly, and if you do that, you're going to wind up with the integrand into expression that's entirely in terms of sine x or cosine x. Then apply the reduction formulas that we did in the previous section. Okay? And that's what you got to do. So basically, double angle formulas are your friends, and use them. And we did it in in example 4. Let's do it in example 5. Okay? So let's see. I don't think. Yeah, this is going to be this one. Okay? Let's us do it first, and then we'll use that. So let's clear all that ink, and let's do example 5. Evaluate this. Okay, it has nothing to do with that one. The integral of sine squared x cosine 4th x. Dx. Okay? Now, here both your m and your n are even. M is equal to 2, n is equal to 4. Now, here's the hint. pick the one that's the smaller. M is less than N. Okay? Now this one is the smaller, sine squared, that's the smaller power. Write that in terms of cosine. Okay? And we know that already. Okay? This will be 1 minus cosine squared x times cosine fourth x dx. Okay? Okay. Now, that gives you an integral just in cosines. Okay? Okay? And that will be the integral of cosine fourth x minus cosine sixth x dx. Okay. Now, they said use the half-angle formulas, but they're going to proceed not using the half-angle formulas, at least for now. Okay? So that little rule at the bottom, they said use the double-angle formulas. They're going to do it without doing that. They're going to use your reduction formulas, okay, that we did back on page 376. There's the cosine nx. Okay. On this one, go with the bigger number now. We're going to do the cosine sixth x. Okay? So we're going to do that first. So let me just break this down. This will be the integral of cosine fourth x dx minus the integral of cosine sixth x dx. Okay? Now, let's start with the 6. Okay? By the reduction formula we did before, this will be integral of cosine fourth x. We're going to come back to this in a minute. We're not going to throw it away, but hang on to it. Minus. Now, what's the integral of cosine? All right, De Silva's here. Okay. I was tired of talking to myself. Okay. So, got it. Okay, then let me get things changed around a little here. Nobody's here to save the projector, because no one's here to see it. I'll do the lights just because it's really hard to read over here in the dark without any lights on, so I do the one closest. But y'all are here. Do this. Now.
Dr. Charles.
Yes.
Can we see the quiz? Like I saw you put the marks on the grades.
Okay, say that again.
I saw you put the grades on.
Right.
Can we see the quiz?
Yeah, I can't return it to you because one person still hasn't turned it in. But I can let you see it for sure. So here you go. Okay. Now I've already given you test 2, haven't I? Or have I?
Yes.
Okay, good. I want to make sure we're in the next chapter now. Okay, now if Marcus comes in, I can let him see his too.
Yeah,
but if the other, okay, if and when well, no, I have it here. So there it is. De Silva was asking me to look at the test, and you can see it, but I have to have it back because I still got one out, so I don't want the correct answers floating around out there until I get all of them in. You certainly can look at them now. Now, I'll be glad to work with you on those, but I can't do it on this because, again, the other person would be able to see and hear the correct answers. So I'll have to do it in office hours. Did you see it? Okay. It was one type of thing you did repeatedly that really messed you up.
I mean, I think I did something wrong there.
Yeah, but it was a very common error you did over and over again.
Because I didn't understand the lesson that much, but I understood most of the part when I'm doing the,
Right.
when we discuss the
Right.
Some part like, yeah.
But it's,
That's surprising. That much low mark. It's really low.
what's that?
The mark is
Yeah.
very low.
Well, I just figured you probably weren't going to be happy with it, but but like I was trying to say, there was one error you kept doing in several problems, and the basic concept you had right, but that error kept blowing your answers. So, I didn't have as much work of yours to deal with, so I couldn't mark it on your work. All I could write was your answer. So if you turn in work, I can show you where they made the error. Yeah. Okay. All right. What we were doing was, and now I need it back, the test back. Yeah. Okay. Especially if Theo comes in, I'll put the correct answer out there. Okay. All right. Okay. What we were doing is this problem here, this example 5 at the bottom of page 380, and I'm on to the top of page 381. It's the integral of sine squared x cosine fourth x. And before y'all came in, I went over the 3 cases they deal with. If either one of these is an odd function, I mean an odd power, either one of them, odd power, real easy to do. I mean, relatively easy to do. Pull out one of them, make them all even, and then use trig identities to get them all into one function, and then the other function is the derivative of that, so you can use substitution and go. Now, when they're both even, that's a little bit more difficult, okay, or a few more steps, I'll put it that way. Okay, these are both even. So what we do is pick the smaller of those two numbers, of those two powers, sine squared. We know that sine squared is 1 minus cosine squared, right? And then you multiply that by the cosine fourth x, okay? Then multiplying that through, you get cosine fourth x minus cosine 6x dx. Split that into 2 integrals. The first of those is cosine fourth x dx minus the integral of cosine 6x dx. All right. Now, this is right about where y'all started coming in. Leave the smaller one alone and deal with the bigger one now. The integral of cosine 6x dx. And what I said, and there's several ways to do it. The hint or the thing on the side margin says use the double angle formulas. But the problem says use the reduction formula. Either way you want to go. The answers will look different, but they'll be equivalent. Okay? If you're doing the reduction formula, turn back to the end of the last section, page 376, and that recursive reduction formula is near the bottom, right above the summary for cosine nx. And we're doing the larger one, which is a 6x. Okay? And that's where we left off. So that formula is cosine nx, where n is equal to 6. That's going to be, now this is a minus sign in front of this, so I'm going to pull that up. 1 over, in this case that would be, we're doing cosine 6x, huh? We're doing the recursive or reduction formula on near the bottom of page 376 with n equals 6. So that's 1 over 6 times cosine fifth, okay, fifth because it's n minus 1, x sine x, okay? plus n minus 1, which is n's equal to 6, so n minus 1 is 5 over 6 times the integral of cosine fourth x dx. Now, I hope you see now why we started with the bigger one. Because here we have a cosine integral of cosine fourth x. Here we have 2. Now, they got coefficients, so we have to deal with those. But you see, these can be used. Now, all that's within the, the entity that's got the minus in front of it. So let's clear that parentheses or grouping symbol. That'll be the integral of cosine fourth x dx minus 1/6 cosine fifth x sine x minus, because the minus changes that, 5/6 times the integral of cosine fourth x dx. Okay. Now, these two you can combine. This is 1, or 6/6 minus 5/6. That'll be 1/6 the integral of cosine fourth x dx minus 1/6 cosine fifth x sine x. Okay. Now we got a cosine fourth x. Let's use the reduction formula on it. So the 1/6 is out front. Now, integral of cosine fourth x dx. That would be what? From your reduction formula. One over bottom or near the, okay, yeah, you're in the old book. The last section, 7.1, just before the summary. Is it there in yours? Okay. On yours, it's on page 376, near right above the summary. So that will be what? We're doing integral of cosine fourth x dx. 1/6 is out front. This will be 1 over n. N now is 4. 1 over 4 cosine, second? Yeah, cubed, x sine x plus 3 over 4, very good, the integral of cosine squared x dx. Okay. That is all cosine fourth. And then we have a minus 1/6 cosine fifth x sine x. I'm sorry, my pen's not writing. I don't know where. Ah, there it is. Okay. I think they got it all on there. It was very, very, very slow. Okay? Now, I just don't have enough room on these little slides. So I'm going to come up here and erase here. Okay? In fact, I think I'll erase 2 lines because we've already done them, used them. Goodness, the eraser is not erasing. There we go. I'll erase everything above this. Okay. Sorry this room's so cold. They have a lousy system here of supposedly regulating it. They don't. Okay. Let's combine what we know here. 1/6 of 1/4 is, 1/6 times 1/4 is 1/24 cosine cubed x sine x plus 3/4 integral of cosine squared x dx minus 1/6. Nope, whoop, whoop, whoop. That 1/6 is that's a 1/24, which would then be 1/8. Sorry, that's 1/8. Okay. Another way to look at it is this way. Remember, this 1/6 times everything in here. When you multiply it by here, the 3 will go to 6 twice. So, in other words, the 1 up there, 1, 2 times 4 is 8. So 1/8 that. So that's up there. Minus 1/6 cosine 5th x sine x. Okay. Now, you can put the two non-integral terms together if you wanted to, or just deal with the integral term. Now you have a cosine squared x. If you go back to the section we were just on, now I don't know where it is in your text, but in yours, cosine squared is at the top of this page 380, right under sine squared. So there's another formula we can use. Now that shows it in two forms, either the double angle form or the single angle form. Since we've been using single angles so far, let's use the single angle form here. So this part, in fact, I'm going to write both of those together. 1/24 cosine 3rd x sine x minus 1/6 cosine 5th x sine x plus 1/8. Now we'll do the cosine squared. Okay, the second one of those, and that is, can you read that? They both start this way. X over 2. Okay, now where that comes from is our double angle formula, but we're using it but then coming back, so that'll be a plus 1/2. My pen is so slow. Okay, there it is. Sine x cosine x and then they do a plus c. I'm going to do a plus c at the end outside the parentheses. It doesn't matter where that is. Okay. That now gives us our final answer. Okay. And there's several ways you can write it. I'm going to write that linear term first. That would be 1/16 times x. If my pen will ever catch up, there it is. That's the 1/8 from there. And then I'm going to do these other terms, plus 1/24 cosine cubed x sine x minus 1/6 cosine 5th x sine x. Now I'll go back to that last term, plus 1/16 sine x cosine x plus c. Now, that's not a very logical way to write it, but it is a correct answer. Now, a part of me would want to factor out the 1/24 and then leave whatever other fractions you have there. It's not necessary to do it. Another part of me would want to factor out all those sine x's from these three terms and separate those out and leave just your cosines, and then probably put them in decreasing order of the power of cosine. Or you could factor out sine x and cosine x and then just leave a cosine squared here and a cosine fourth there, but put it in some other order. It really doesn't matter the different ways you put it. That, though, is your answer. Now, let's see how the book did. They may look very different from this, but I think it'll be equivalent. So let's see what they wound up with. They wound up with a -1/6 cosine fifth x sine x. That's that term. Plus 1/24 cosine cubed x sine x. That's that term. Plus 1/16 sine x cosine x, if they put cosine x sine x, which is what I would have done, but they did otherwise. Plus 1/16 x plus c. So yes, we did get the same answer, just in a little bit different order than what they did. I just kind of don't like leading off with a minus sign, but they don't have any objection to that. So that's one way. If you use case 3 and the double angle formula, you would have gotten the same answer. It wouldn't have looked the same, but you split off sine x cosine x here, and that gives you a sine 2x, so you could have had a different looking answer with that, okay? But this is just as good of an answer. You will not get it wrong there. When you put the double angle formula in there, it actually, I don't know, in some ways looks a little bit simpler. You'll get one term in sine 2x, one in sine 4x, and one in sine 6x. Now, I can't see, just looking at this, exactly where all those come from, but I'll take your word for it. That answer is the same as what they have. Okay? Now, those are sines and cosines. Any question? Oh, let's move on and see a part of this problem they showed on the slide. So let me zoom in on that so you can see it. This was that early step that we did. I wanted you to actually do it. So when we had this step, we changed the very first step, changed the sine squared x to 1 minus cosine squared x. And when we do that, then that gives you a cosine fourth x minus cosine 6x. Split that into two integrals. Then over cosine fourth minus over cosine 6. Okay. So the rule is when they're both even, you pick the smaller. Now if they're the same, it doesn't matter which one you pick. And then proceed like this. Once you get it all in terms of one trig function, this one is all cosines, then pick the larger one, okay? And start doing your reduction formula based on that. Okay. So that was their first step, which is basically the same thing we did. All right. Now, I think this shows a little bit more. Hopefully about the same. They're skipping a bunch of steps here, but they're showing their final answer. Yeah. And this will be minus 1/6 cosine fifth x sine x, which is one of the terms we had, plus 1/24 cosine cubed x sine x, which we had before, plus 1/16, and I had written it sine x cosine x, you can write it cosine x sine x, that's fine, and then plus the 1/16 x plus c. So that is the final answer, which agrees with what we got, just in a little different order, but that's all. All right. Now, here's another problem. not quite ready for that yet. So let me back off of that and write on this slide. Okay. Here's example 6. Any question on 5? Example 6. It says to derive these two formulas. Okay. The first of these is the integral of tangent x dx. Okay? If you were asked to do that, what would be your first step? Okay, I can almost see Marcus say, look it up on the table. Yeah, I thought, no, okay, we're going to derive it first, then after this you can look it up on the table. But what would be your step to actually do it? Hint, trig identity. Second, we're going to substitute, but we first do the identity. What is tangent in terms of a sine over cosine? Perfect. So this is the same as the integral of sine x over cosine x dx. Okay? Now we start considering, as Marcus said, a substitution. What do we use to substitute? The cosine. We pick the innermost part, the most difficult part of the problem, most complicated part, which in this case is the denominator. So that's what we're going to let the u be, or whatever you want to call it, just don't call it x. Let u equal cosine x. Then, what's the next step? du is equal to there it is. Say again? Negative sine x dx. Okay, the pen is really slow. Okay. Well, we have a sine x dx. We don't want the minus, so we're going to move the minus to the other side and put it with the du. Okay? All right. So now what we have in terms of u is the integral of, it's going to be minus the integral of u, I think it's more like, yeah, du over u. Okay, and what's the antiderivative of that? Okay, if you wrote it that way, you'd have a u to the minus 1 du, right? Okay, and then the rule would be, add 1 to that, that would give you u to the 0 over 0. Yeah. You can't divide by 0. So there's a special thing for this one. What is the antiderivative of 1 over u du? What function, when you take the derivative of it, do you get 1 over the argument? The what? ln, exactly. This is the natural log. So this is minus the natural log of u. And you have to put absolute values around it, unfortunately. Okay. So, and we can put the plus c there. I don't think it's going to hurt anything. Now we substitute back in. Since this is an indefinite integral, we have to substitute back in. What was our u? So it's natural log of cosine x plus c. Okay. Now another way you can write that is the natural log of cosine x to the minus 1. You know, take that minus and move it in. Okay? Which is the same as, and that's plus c, that's the same as saying the natural log of 1 over cosine x plus c, and you, probably all these should be in absolute value bars. Okay. Look, what's 1 over cosine x? Secant. It is a lot like secant. Okay, that's the log of the absolute value of secant x. There is your integral of, got to find it, here we go. Tangent x is the natural log of absolute value of secant x plus c. Okay, now, the next one is not nearly so clear, okay? In fact, I suggest on this one, just look it up. But we'll do it once, and after this you can always look it up. The integral of secant x dx. Okay? Now, our earlier thing would say to rewrite this as 1 over cosine x dx, but we don't have anything to substitute there because you don't have a du. So that's not going to work here. And how you get it to work is use a trick. Okay? So many of these things use tricks. That's why I say look it up, because who wants to remember the trick? Okay? But here's what the trick is. It seems bizarre, but it works. Multiply numerator and denominator of that integrand by secant x plus tangent x over secant x plus tangent x. Who would think of doing that? No one in their right mind. That's the answer. The integral of secant x times secant x plus tangent x over secant x plus tangent x dx. Yeah, that's what I would think of right off the top. Yeah, why not? Yeah. Okay. The interesting thing is what that does for you. If you multiply through by that, and it really does work, this will be the integral of secant times secant is secant squared x plus secant times tangent is secant x tangent x. Okay, all over secant x plus tangent x dx. Okay, now what would be your step from there? This is going back to the top one. Doesn't look as obvious here, but guess what? If you let your u be that denominator, okay, see what your numerator, see what it becomes. Let u, just like we did above, equal the denominator, secant x plus tangent x, okay? Then, what is du? You know what derivative of secant is? It's what? No, the derivative of secant x. Not what is secant x, but what's the derivative of secant x. Okay? Now I believe this is on your back inside cover. Okay, the very, very, very back is your table of integrals, and then if you're going there anyway, you ought to just use that and look up secant x. But we're not doing it that way. Go back one more page to the differentiation. And the differentiation of your trigonometric function, derivative of secant x is, number 17, secant x tangent x. Oh, that's in our numerator, isn't it? Plus, what's the derivative of tangent x? Secant squared x. That's in our numerator. These are all both multiplied by dx. And sure enough, that's your numerator, isn't it? So what we have here is the integral of du over u, right? U is the secant x plus tangent x. Your du is the secant x tangent x plus secant squared x dx, which is exactly your numerator. And guess what that antiderivative is? Hint, hint. You've just seen it. L in U. That's the log of U. Absolute value, of course. Okay? But what's our U in this case? Secant x. Yeah, plus tangent. I couldn't find it. Plus tangent x. Okay? And actually, these should be absolute value bars because you can only take the log of positive numbers. Can't even take the log of 0. Okay, they have to be positive. And then the plus c, exactly. Just starting to say that. And that's it. What a tricky substitution. Well, a trick that you had to do before you could do your substitution. So, this gives you your integral of tangent x and your integral of secant x. And guess what? From now on, if you don't remember them, look it up. I mean, I don't see any reason to go through all that again. Tangent, though, was pretty easy. Secant, you have to remember the trick, so why don't you just look it up? I mean, it's just as easy. If you got tables, use them. Okay. And by the way, if you flip the page in the new text, new edition, is page 382, you'll see right across the page is your table that we partially are referring to. And if you go down to number 13, you see that is indeed your secant x, and you see exactly what it is. Go up to 9, and you'll see the tangent x is log of secant x or negative log of cosine x. So either way you want to do it, both plus c. All right. So the next 3 examples are doing closer to what I feel like you probably should do on a lot of these. Okay. Is using table of integrals. So let's do example 7. Okay. Not involved with that yet. Also, sorry. About this time of morning, my head just clogs up again. I do not know why. I think it's the cold air blowing in on me, but I can't do anything about that. Here is what we're asked to evaluate. This is a definite integral from 0 to pi fourths. Tangent cubed x dx. Okay. Now, all we did was a tangent x. We didn't do anything about a tangent cubed x. And without doing anything else, just use the table, okay? Especially since it's right across the page from you, or maybe you have to flip a page. You'll see one that's similar to it. And that's number 9 was just tangent x, which we already derived, but number 10 is tangent mx. So in this case, what's our m? Uh, 3, right? Tangent mth x, where m is equal to 3. And what does number 10 tell you the answer is? Tangent. Okay. You might have to flip. Let me hold up that next page that you have. No. Okay. Turn one page. No, this way. You see that table? That's what we're looking at. Yeah. Okay. Yeah. tan squared x.
That's why I was
Thing.
so confused. I don't know how you get like all that formula, but yeah. Now I
Right.
see.
Okay. Over
Over 2
2. Okay. Minus
minus
integral
and 10
tan what?
10x
Tan x. Okay. Dx. Okay. Now, here's what you do when you are using these tables. Okay. When you have something outside the integral, you evaluate that from 0 to pi fourths, whatever the limits there of your integral. And then on the inner integral, you write that down again, 0 to pi fourths again. Okay. Now we can evaluate that first one, or can we? Oh, that's a tangent squared. This thing went crazy on me. And,
You can take 1 over 2.
okay, yeah, this is tangent squared. Okay. All right. What is tangent of pi fourths? Pi fourths is 45 degrees. What is the tangent of 45 degrees? Is 1. Exactly. That's what it is, 1. Okay, so that'll be 1 squared over 2. That would just be 1/2. And tangent of 0, by the way, is 0. Okay, so that's done. Minus, now, what is our antiderivative of tangent x dx? We just did it not long ago. Remember what that was? Natural log of what? Okay. If you do the ln of cosine, it has a minus in front of it, so that would be a plus then. Ln of cosine. Okay. And that you evaluate from 0 to pi fourths. And that's a perfectly good way to do it. Okay? Now, since you're going from 0 to pi fourths, from 0 to pi fourths, cosine's always positive, right? Everything positive in the first quadrant. So you can lose the absolute value signs. So you have the 1/2 from here, plus, because if you're doing cosine, that's a minus. Yeah.
It should be tan square, right? Up there. Did you take that scan?
No, remember, I think Marcus answered that. It's, look at the formula there. It's minus tan of m minus 2. Our m was 3. Minus 2 is 1. Yeah, okay. Oh, yeah. It was, and when I erased something, it erased too. I'm sorry. I know what happened. If I hold the pen down too long, this box comes up. And then what I've written, when the box goes away, it takes that away. I had written a 2 there, and when the box went away, it took away my 2. It's a weird thing about this. But that's it. But we've already evaluated that. The tangent of pi fourths is 1. You square 1, and you get 1 over 2. So that's where that 1/2. So that's already done. Okay? But yeah, you're right. It should have been there, and I thought I had written it there, but then it disappeared. when the box went away, so just doing some weird things. But this is now minus, if you do the integral of tangent x, it could be minus the log cosine, so that minus becomes a plus. Now you do the log of cosine pi fourths minus the log of cosine of cosine of 0. Okay, so that 1/2 is still out there. Plus, now what is cosine of pi fourths? I said, what is cosine of 45? Did you know that?
Yeah, it's 45.
Well, pi fourths is 45 degrees. What I'm saying is, what is the cosine of that? Either one of them. Either in radians is pi fourths, or in degrees is 45 degrees. What's the cosine of either one of those? Don't have to talk to your trick teachers. Okay. Cosine of pi fourths, or cosine of 45 degrees. Either one. Square root of 2 over 2. Very good. Now, I'm not going to write it that way. I'm going to write it as square root of 1 over square root of 2. Is that okay? Okay. So I'm going to put the log of 1 over root 2. There's a reason for that. We'll come back to in a minute. Minus, what's the cosine of 0? Sine of 0 is 0. Tangent of 0 is 0. What's cosine of 0? 1. Okay, and what's the log of 1? It's the log of 1. 0. So that last part goes to 0. Okay, so forget it. Okay, not there. Now, the reason I wrote it that way, this is 1/2, and you could write this way, plus log of 1 minus log of root 2. Do you know that identity? The log of a quotient is the difference in the logs. The log of the numerator minus the log of the denominator. Did you know that? Okay. And what's log of 1? 0. So this would then be 1/2 the minus log root 2. Which, there's still another way you could do that. You could write that as 1/2 minus the log of 2 to the 1/2, right? Isn't that what square root of 2 is? Okay, and then you can write that as 1/2 minus 1/2 log 2, right? There's another log identity, log property, that if you have the log of something raised to a power, pull the power on the outside if you have it. And that then can be written as, there's just all these different ways to write it, 1/2 times 1 minus log 2. There's a ton of ways to write the answer, and it doesn't really matter how you do. Which way does the book write it?
1/2 minus.
They do 1/2 minus the log of root 2. So that was this one right here. That's perfectly fine. Any of those are correct. Now, before we go to example 8, they have another margin note. And again, these should be on a slide, and they're not, so I'm going to write them in. So I'm going to clear all my ink. If y'all got this one down okay?
Yeah.
Okay, so I'm going to erase all that ink and write down these margin notes. This is when you're integrating some combination of tangent to the mth x, that's the m, times secant to the nth power times x. Okay? And these look a lot like we did before. Case 1. M is odd, and n is greater than 1. Okay. So in other words, if n is 0, go back and just do tangent mx. Don't even mess with this. If n is negative, don't even mess with it at all. I mean, we haven't done any with those. Okay? So this means that basically when m is odd and n is any positive number, including 1, just not 0 or negative. Okay. Then what do we do? Well, it's a lot like before. Factor out one of those tangent x's, okay, and that will give you a tangent x times a secant x, okay? Rewrite that, and then it'll leave you a tangent to some even power. You know, we're saying m is odd. Factor out one of those and make it a tangent. The other will be a tangent to the m minus 1, which then, of course, is even. Well, tangent of an even power is some power of tangent squared, right? And then you just make that tangent squared 1 plus, tangent squared is secant squared minus 1. Okay. Y'all knew that identity or not? Okay. Start with that basic Pythagorean identities. Sine squared x plus cosine squared x. You know what that is, right? 1. Okay. Now, divide both sides of that, everything on both sides of that, by cosine squared x. What does that give you? Sine squared over cosine squared is tangent squared x plus what's cosine squared over cosine squared? 1. And what's 1 over cosine squared? Secant squared. Right? Now subtract 1 from both sides. And you have tangent squared x is equal to secant squared x minus 1. Okay? So, what you do is when you factor out one of your tangents, that leaves you an even power of tangents, because m was odd. Even power of tangent. Take that and make that tangent squared raised to some power, whatever. Give me an even number. 2. Okay, if that was tangent cubed x secant any x, then take one of those tangents out, and that leaves a tangent squared. Tangent squared is secant squared minus 1. Okay? And then you have a tangent x left over, a secant x from here, and then you have the rest of the secants there. If this n was equal to 1, you've already taken care of. If n was greater than 1, then whatever you have left off the secant. So this would be a secant squared plus minus 1 times the secant, or secant to some other power, times the tangent x secant x. Tangent secant x, that's the derivative of secant. So you can do a substitution from there. We'll come back and do one with that. So that's case 1 with m is odd and n is any positive number. Okay? Integer. Okay? Case 2. Case 2 is n is even. Okay? It doesn't matter what m is. If n is even, then what do you do? Separate out a factor of secant squared. Well, n is even. That could be secant squared, or it could be secant to the 4th, secant to the 6th, secant to the 16th, secant to the 28th, or whatever, 94th, doesn't matter. Pull out one secant squared, okay? And then what you have is the rest of these secants, you can use this formula, except use this formula, and keep a secant squared by itself. All the rest of the secants, write in terms of tangent, multiply by this tangent, and then you have everything in terms of tangent with a secant squared, but the derivative of tangent is secant squared, so you have a substitution. Okay, so that works pretty nicely. All right, so those aren't bad. All right. And then here's the case 3. This is the difficult case, or just a little more involved. Case 3. Okay? M is even. Okay, see, if M was odd, you could use case 1. Now M is even. But you also have N being odd. Oh boy, what do you do with that? Okay? M even, N odd. All right. M is for tangent, N is for secants. Okay? Well, we'll go back and use that identity there, the middle, this one right here. Tangent squared plus 1 is equal to secant squared. Okay? Because that M is even, we can get all of our tangent squareds, tangents, in terms of secants. Wait. No, I'm sorry. I think that's what we do. No, I'm sorry. Use the bottom. Tangent squared is secant squared x minus 1. Okay? That. Okay. And then, because M is even, get all of these tangents in terms of secants. You already got secants here with the odd number. Get all those others. And then you have an integral only in terms of secant squareds. Okay? Okay? And then you use your reduction formula, which is number 14 in your book. So you look it up in a table. Secant mx is, there you go. And just use that reduction. Okay? So there's no way to do it independently, but you can do it using the table. But that's how you proceed. All right. Let's do an example with those. Can I go on and erase the work here? All right, let's do example 8. Evaluate this one. Okay, has nothing to do with that. The integral of tangent cubed x secant to the 5th x dx. Okay, now which of these cases you want to use, or how would you proceed? Very first case there says, what do you do if M is odd and N is anything? That's the one we use. It's a pretty easy one. Okay? It says tangent, the M is odd, the tangent power is odd. Pull out one tangent. Okay? So this is going to be the integral of tangent squared x secant 5th x tangent x dx. Right? Now, you can take this tangent squared x. Remember, there's a identity. Remember what that one was? Secant squared x minus 1, right? So that we're going to put in for the tangent squared. This already has secants only. Pull out one of those two, so let's leave this as a secant fourth x, and now we have a secant x tangent x dx, right? All right. Now, let's multiply these together, and that's going to be the integral of what? 6x minus fourth x times secant x tangent x dx. Okay? Now, I think probably best to break this into two integrals now. This is going to be the integral of secant 6x secant x tangent x dx minus the integral of secant fourth x secant x tangent x dx. Okay? Secant x tangent x dx, they're the common factor. Pull them out and then do just the others. Right? Now, what you reckon we might do here? Substitute. And what will you substitute? U equal secant x. You got it. Then du is equal to, what's the root of the secant x? Secant tangent. Secant x tangent x dx, right? So what is your first integral going to be? Integral of, second, u to the 6 du, okay, minus, now, let's just imagine we did the same thing with the other one. And what would that be? Integral of u to the fourth du. And what's the first one? U to the 7th over 7 minus u to the 5th over 5. And then you'd have a plus c. Very good. And what's u to the, u in both of those cases? Secant x. So that would be secant to the 7th power x over 7 minus secant to the 5th power x over 5 plus c. All right. Let's see if that, oh, look at them. They got it right. Good for them. See how that works? That's with any time that tangent is an odd power. Just separate it out and go that way. Okay? Now, let's do, what's my next slide? This must be something from, oh. That's the one we just did. Okay? I wanted y'all to do it first and then we'll see. And they do it the same way we did. Okay? The integral of, oh no, this is a different one, isn't it? Sorry. Oh, this isn't quite the next one, but it's almost. So forget this for now. Okay? Go back one. It's what?
That's example 7 in my book.
It's, okay. It's almost like 9 in this one, just a little different. So we'll do 9 and I'll point out the difference to you. We'll erase all that ink and go with this one. Evaluate this one. The integral of tangent squared, see it starts the same way, x secant fourth x. Okay, yeah, yours is third. In the new edition, it's fourth. And since I think Theo has the fourth edition also, and I know you do, we'll do this one, and then we'll go back and see how it changes. Okay? So, goodness, my eye. In this case, they're both, well, okay, they're both even, but specifically n is even. The secant one is even. If the secant is odd and m's even, there's something else you do, but this is n is even. So we use the second one of these. Okay? So what we do in this case, goodness, my eye hurts, is separate out one of these, or two of these actually. So this will be a secant squared x secant squared x. You okay with that? All right. Now, in yours, that was odd. So this is going to be a very different problem. I thought it was going to be similar. So we'll come back and do that one too. Okay. So what are we going to do now? We can get this secant squared in terms of tangent squared. What was, that identity? Do you remember it? Tangent squared x plus 1. Leave that, secant squared by itself with the dx. Okay? So what that gives you is integral of tangent squared x times tangent squared x plus 1. That's for the first secant squared x. 10 times secant squared x dx. Okay? And this will be the integral of tangent fourth x plus tangent squared x times secant squared x dx. Okay? Now, guess what we're going to do now? Substitution. And what will it be? Let u equal tangent x. Okay? Then du is equal to secant squared x dx. And that's exactly what we've got there. So what do we have here? The integral of u to the fourth plus u squared du, right? Because the secant, yeah, because that is your du, right? That is a u, not an a. And what's that antiderivative? U to the fifth over 5 plus u to the third over 3, and then plus c, and then plug in what they are. What is your u? Tangent fifth x over 5 plus tangent cubed x over 3 plus c. All right. So that was the case 2, when n is even. Factor out one of those secant squared. The rest of them get in terms of tangent squared, multiply them by your tangent. You got it. Power formula. Okay. Now we'll do the one from your text. Okay? And, okay, before we do that, let's go, no, this is that. Okay. After we do this, we'll do it. Let's erase all this ink. And yours was the integral of tangent squared secant cubed. Is that right? Yes. Tangent squared x secant cubed x dx. All right. When m is even, but n is odd. Okay? Okay. going to do here is use that second trig identity we had up there, that tangent squared x. Remember what that was? No, in terms of secants. Secant squared.
Yeah, x minus 1.
Minus 1, exactly. Okay. Now this then will become the integral of secant squared x minus 1 times secant cubed x dx. Right? Now, that will be integral of secant to the fifth x minus secant cubed x dx. Now this one, break into two integrals. Integral of secant fifth x dx minus the integral of secant cubed x dx. All right. Now you go to the table. There's no easy little way to do this. Go to the table and do it with the fifth first. This will be the integral, and this is in my table it's number 14. Is that the same in yours? Secant mx.
No.
What is it in yours?
20.
Huh? 20th, okay. And this one, for some reason, well, whichever it is, this is the secant mx dx, right? Do it with 5. So that'll be what? I don't need another. Yeah, let me erase here. Okay. Okay, it starts with a sine x. No, tan x. Yeah, tan x. Times secant to the second cubed x all over 4. Very good. Plus 3 over 4 times the integral secant cubed dx. Now we have then a minus integral of secant cubed x dx. You see, we were just doing the secant fifth, and this was all secant fifth here. And then we had the minus secant cubed. All right, so what does this produce? Tangent x secant cubed x over 4 minus, because this is plus a 3/4 minus a 4/4, that's minus 1/4 secant cubed x, right? Integral of secant cubed x. See it? Okay. Now this is tangent x secant cubed x over 4 minus 1/4. Now we do that same formula again with a 3. And that will be what? Tangent x secant x over 4. Okay, that was still there. Plus, oh, I'm sorry. Yeah, I'm sorry. I used the first 4, but I forgot to do the second one. Okay, that now reduces to 2. Yeah. Okay. Plus 1 over 2 times the integral of secant x dx. Okay? And we remember what that is, don't we? This will be tangent x secant cubed x over 4 minus tangent x secant x over 8 plus, no, it's a minus, sorry. Okay. Can you see? Sorry. Because that 1/4 multiplies across there too. Minus 1/8. Now, what is the integral of secant x? Remember it? If you don't, look just up 1 at the table. Second, natural log of absolute value of secant x plus tangent x. Plus c, because these are all indefinite integrals. Okay, is that anything close to what your book has? See, I don't have it in mine. Your what's that?
The answer is correct. It's right.
It is, okay. 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 I couldn't read my writing there. Okay. That's exactly what we get. Now, we didn't have that in ours, but since she had it in hers, we do that. Now, and that's what this next slide showed, is how to set up what we just did. So, since maybe my writing wasn't the very best in the world, close to it, but maybe not quite. The first step there was when this is even in that side, pull out a tangent squared and substitute this for it. And if that had been tangent to the 4th or to the 18th or anything even, then that would be a tangent squared to the squared or 9th or whatever. And then this would be that to the square root of 9 or whatever. But the deal is you get everything in secant squares, in sequence, okay? And when you do that, then you use your table to get one secant square. And that's exactly what we did. Okay. So, is this the same problem? I think it is. Zoom in. Okay. So that gave you, yeah, that was the first part, tangent x secant cubed x over 4 plus 3/4 integral of secant cubed x dx minus secant cubed x dx. And then this is just like we did before, 1/2, 1/4 tangent x secant cubed x minus 1/4 secant cubed x. Then go back and plug in that previous one again for secant cubed x. Okay? Now, what they don't show here is example 10 in our book. Are we out of time? Oh, okay, you're just putting things away. Okay, example 10. Here's a completely different kind of integral. Okay? Evaluate this. And it's a definite integral, so that's one difference, but that's not the main difference. Okay, ignore this. And what we have is the integral from 0 to pi of sine of 4x cosine 3x dx. Now, on your table of trigonometric integrals, do you have one with sine mx cosine nx? It's probably near the bottom.
Yes.
You do? You know, on mine it's number 17. It's yours is 24. Okay, we're going to use that one. And since we have different books, let me write it down. This was the sine and cosine. Here's what we're going to use. The integral of sine mx. Now this isn't raised to the m. This is mx cosine nx. That's not a power. That's a multiple. Dx is equal to cosine m minus n x over 2 times m minus n minus cosine m plus n x over 2 times m plus n plus c. Now, what's required here is m cannot equal either plus or minus n. In our case, it's not, because 4 is not equal to plus or minus 3. So we're okay. So we're going to plug and chug exactly what we got from below. Now, I hope this isn't too confusing to do it this way. I'm going to pull out the coefficient first, the denominator first. That denominator is 2 times 4 minus 3, right? So that's going to be 2. 4 minus 3 is 1, so that's going to be 1/2 cosine of 4 minus 3, right? Cosine x. Okay? You buy that? Okay. Just to shorten things so I can keep it as simple as possible. Cosine x. That's the first term. Minus, now I'm going to pull out that fraction again. It's a 1 over 2, but m plus n is now 7. So that's a 1 over 14 times cosine of 7x plus c. Okay. But on each of these, we evaluate from 0 to pi. On this one, from 0 to pi, because this was the definite integral. So guess what? We don't need the plus c anymore. Okay? Why did I even write it down? Because this is a definite integral. Sorry, I wasn't paying attention. Okay, so let's do that. That'll be 1/2. What is cosine of pi? No. Cosine of 0 is 1. Cosine of pi halves is 0. And cosine of pi is -1. Right, okay, got it. So that's a -1 here. Okay. Minus the cosine of 0 is 1. Okay. So there's the first part, minus 1/14 times, now, what's the cosine of 7 pi? Okay.
Do we have to get the pi value and multiply by the 7?
How about let's do it this way. What you're just looking at is at 0 it's 1. Pi is -1, right? Did you leave something? Okay. All right. 2 pi is 1 again. 3 pi is -1. 4 pi is 1. 5 pi, -1. So that comes up being -1. It's an odd pi, right?
Yeah.
So it's going to be -1 again. So that's going to be -1 times, okay, minus a 1 again, right? Because cosine of 0 is still 1. So what do we have here? This is be a minus 2 over 2, so this is going to be a -1 minus 1/14 times a minus 2. So that's going to be a plus 7th. Okay, so that's minus 6/7 is what I think it is. Oh, 8/7. Yuck. Oh, yeah, that is a minus. Sorry about that. No, minus a minus is plus. And that does look like it's going to be a 1/7. So -1 plus. Let me see how they did this. Oh, wait. They lead off with a -1. Oh, I misread the problem. There's a minus sign in front of that. My eyes are not good. At the very beginning, there's a minus. So that means this is a minus right here. Yeah, I didn't either. Sorry. So that meant that was a minus, so that's a +1, and that's a +1/7, and that's how they get +8/7. Right. Good deal. Sorry about that. Very easy problem. I completely messed up because I didn't even see the sign. I don't know where my head is. Now, I don't know if you remember in trig class, did you take trig here or somewhere else?
I don't trig here.
Okay. I don't know if you remember one of those chapters in the trig book, in the pre-calculus algebra book that had trig in it. It had something that they had product to sum formulas and sum to product formulas. And they had that one little section, they did it once. He said, you'll use this in calculus. This is the only time I ever remember using it in calculus. And it's not worth memorizing. I looked it up in the thing. Yeah. So anyway, that's how I suggest. Okay, and that led us then to the next slide, which was this table of, now in yours it's 25, and in this one it's 19, but notice the first 8 aren't listed here, and the first 2 aren't listed in our book. So you really, I think these are the same ones, they're just numbered differently. Okay? So you'll, for 1 through 8, you turn back into the section, and you'll see, I think, 2 pages or 3 pages ahead of this, you'll see numbers either 1 or 2 or 7, yeah. So that's where the others are. You'll find them in other parts of the text. Okay. So those are your table of integrals. That finishes the section. Do you want to do preliminary questions? Do we have time? I don't know. What. It is 11:10 now. Do you want to do these next time, or do you want to go and start in 7:3? Okay. Yeah, I will mark that we will, and if y'all say, no, we've already done them, then you don't have to. So it's up to you. If you do preliminary questions and have no problem with them, tell me and we'll move on to 7:3. If you don't, tell me and we'll do preliminary questions first. Okay, good deal.
I have another question.
Yes.
I mean, I know I made, that is my first time making low amounts. So
And it wasn't really all that low, but okay, I know.
It's low to me,
Right.
I want to get B, I want to get A.
Right. Okay.
So is there any way to make up that test?
I do drop your lowest test score.
Okay.
Okay.
Okay, that's a great thing. Thank you.
Okay. All right. All right.
Because I don't want to, I try to keep up my GPA high.
Right.
Because I can't afford for the university, so I want to try to get a scholarship.
Right.
So right now I have 3.9. I don't
Yeah.
want to get a B for any subject.
Right. Well,
I think having A, all I have is 3 B's.
Right.
So, and this is the final semester that I'm taking here.
oh, really? Okay. Okay. Well, just do the best you can. I know you can do better. And when you see that, I think you'll see you just made that one silly mistake over and over and over. You know, I couldn't figure out why you did it, except just the pressure of the test, probably. So, anyway, all right, we will. Glad to. All right, we will end this.